So today we're going to be talking about some of the most fundamentally important reactions for generating energy, and that's combustion and metabolism. They're very similar, and through them we're able to actually power both our bodies as well as everything pretty much around us. Okay, so let's recap again. So in thermodynamics, we understand that some reactions, depending upon the stability of the molecules, require energy to be input for them to go in the forward direction. So, for instance, cooking an egg or cooking a pizza. And this is the Maillard reaction. So this is the browning of proteins, and this requires energy. It requires chemical transformations to ultimately to cook all the ingredients in the pizza. We also know that there are other reactions that release more heat than goes into them. So even though you start a fire when you're burning wood, it actually generates more heat than the original fire that started it, right? So this is actually, by burning wood, you're actually generating heat. So these are the exothermic transformations. And so burning wood is a great example of a combustion reaction. These are some of the most important classes of reactions that we have. And so a combustion reaction, it normally involves molecular oxygen. Okay, so there we have that. And heat. So usually there's a little bit of heat to get this thing started. And it converts a fuel source to carbon dioxide and water. And it's always exothermic, so you actually are going to be generating more heat than you put in. So even though you put in a little bit, you get more out. And part of that reasoning is because CO2 is a particularly stable molecule, as is water, and as a result, you're generating more stable products than you started with. And so an example might be burning something like natural gas. Natural gas is going to produce a single equivalent of CO2 and 2 water molecules when it reacts with 2 oxygen atoms. Going back to the wood example, so what's going on here? So wood is, of course, cellulose, right, which is a whole bunch of carbon and oxygen kind of linked up together. It's also got some lignins and some other molecules associated too, but we'll just simplify it, and we'll talk about it's mostly cellulosic material, and so you can add oxygen to this and heat, and it will ignite and burn and ultimately convert all of these carbon atoms in the presence of oxygen to CO2, and then hydrogen and oxygen will also combine to form water and energy. So you're going to notice a theme here. So another one that we are very accustomed to is the burning of octanes or gasolines. So this is nothing more than a longer chain version of natural gas, and it's also very similar to the cellulose burning. This is a carbon-based fuel, and so this carbon-based fuel undergoes a reaction with molecular oxygen. In this case, it's using spark plug and it's using an auto engine, but it sucks all this in, and it ultimately comes back out with carbon dioxide and water as the byproduct, and heat. And the heat is ultimately what is going to drive the powering of the engine. Okay, so that's combustion. Let's transition to metabolism. You're going to see how they're very, very similar in many ways. Well, we're going to start this off by asking a kind of a simple question, but an important one, which is how does a human lose weight or gain weight, really? And so I think the answer most people give is you burn calories, but that's actually not a true answer, because calories cannot be burned. They in fact, calorie is energy. It has no mass to it. And so when you're talking about losing weight, we're talking about you actually have to lose molecules from yourself. To lose weight, you actually have to somehow shed off molecules, and then you'll be less massive, right? You'll have less matter in your body, and that is the only way you can lose weight. Okay, so then how do you lose weight? Well, a lot of our mass is stored as fat molecules. These are these triglycerides, and these triglycerides can be burned just like in combustion. You can take molecular oxygen and you can take these fatty acid chains and these fatty acid chains, like palmitic acid or something, will undergo oxidation, and ultimately you'll get out CO2 and water and energy. So this is typically what we talk about when we talk about exercising and getting energy out of burning fat. We're talking actually about a combustion reaction, that we're converting all of these carbons and these hydrogens into CO2 and water, and we're getting energy out of it. So it kind of comes back to, how do you lose weight? Well, you actually breathe out CO2, and you lose weight because the CO2 that you breathe out, it has weight to it. If you don't believe me, weigh yourself right before you go to bed, and then weigh yourself in the morning. You will weigh less because you've been breathing all night long, and you've actually been losing CO2 from your body. People say, well, okay, is there a way that I can, I don't know, lose CO2 faster? Can I breathe faster? And the answer is, yeah, actually, you can go on a run. If you go on a run, you typically burn more quickly, and then you actually exhale more CO2 and water quickly. You'll also notice below that the structure of palmitic acid looks very similar to the structure of gasoline, or even methane. And so once again, in an engine is doing the exact same transformation. It's taking O2 and it's burning it to form CO2 and water, and you get out energy. So you and an engine are doing chemically very, very similar chemistry. This might seem like a silly follow-up question. How do camels make it through the desert? And as a kid, you're always taught, oh, look, they're filled with water, right? They have these humps that are filled with water. No, the humps are not filled with water. The humps are filled with fat, actually. So they're entirely filled with fat. And so if we think about this, this actually makes a lot of sense, that when you burn fat, you produce CO2, but you also generate a whole bunch of water. And so one of the ways that camels can rehydrate themselves is that they actually can burn some of the fat in their humps, and they actually will get out some of the water from those humps. And where did the water come from? It came from the hydrogens of the fat, and it combined with the oxygen that they were breathing. And in fact, if you actually think about it, the Camelback brand of hydration packs, right? So what are they talking about, right? They're talking about the water that is ultimately generated from these humps. Okay, so what have we talked about? We've talked about combustion, we've talked about metabolism, but we really talked about the same kind of transformation, that we have some sort of fuel source. Typically, it's going to be a carbon-based fuel source, whether it's cellulose or glycogen, whether it's methane or octane or a fatty acid. And this fuel source is going to combine with an oxygen and a little bit of heat, and together this is going to ultimately overcome the barrier necessary to undergo a combustion or a metabolism reaction, and you're going to generate the two main byproducts, water and CO2. And then also in the process, this is going to generate lots of heat, and a little bit of that heat is actually going to go and can help out sometimes, especially with combustion, to keep the cycle going, to kind of keep it until ultimately you burn through your fuel. But at least in metabolism, it also can be a way to keep you warm or do other biological important events.